This is an introductory video on chemical kinetics. Chemical kinetics actually deals with three things mostly: its rate of reaction, mechanism, and factors influencing the rate. And here, first, let's discuss regarding rate. A rate actually expressed as change in concentration per unit time. It's the simplest definition for rate. And here we represent change in concentration as delta C and change in time as delta T. The reason why we take time as delta T is because when we consider concentrations as C0 of a particular substance, let's say C0 to C1 to C2 to C3 at respect to time, where we took C0 as a starting point of time as 0 seconds, and as time passes it goes on at a particular instance. When we consider the concentration in this circumstance between C2 and C1, we need to subtract the time between C2 and C1. This is the way we actually get the change in concentration per unit time, and this is the reason why we use delta to represent the changes. And now we have, for those who don't know regarding concentration actually expresses number of moles of particle per unit volume. In this way, we take volume here as liters, and this is what molarity is. And now moles per liter means in a container, let's say at a particular volume, how many particles would be there represents the concentration. The more the particle, the more the concentration. The less the particle, the less the concentration. And here, what is 1 mole actually? For those who don't know, a 1 mole is a count of 6.023 into 10 to the power of 23 atoms or molecules. This count actually seems arbitrary, but this is taken as a standard to understand many things, many phenomena, and many equations. And here, why this arbitrary count actually comes? It's taken from C12, where 1/12th part of C12. When they calculated, there were 6.023 into 10 to the power of 23 atoms in C12. That's the way actually they regard this count as standard for 1 mole count. It's like taking one set as 200 something. In the way here we took 1 mole as 6.023 into 10 to the power of 23 atoms and molecules. And there is another question that we could ask: why actually we need to take rate as change in concentration per time apart from moles per time? The reason is that the rate is considered as change in concentration per time apart from considering change in moles per time, is that uh, when we actually need to find the moles, we need to find the number of particles in some way. To find that, we actually need to consider the act of measuring the moles is with a hidden consideration of volume itself. Without considering it's in fixed volume, it could be in an open space, and it would be hard to actually find number of moles actually dispersed in air. In order to make this understanding simpler, concentration is the best term where we could take for that. And now we have been talking regarding the rate of the reaction. What is actually a chemical reaction? It's a basic question. as it's a first introductory video, I would like to express what is a chemical reaction itself, and even first I would explain what are the things that are not a chemical reaction. The first one is that when a liquid like H2O turns into another phase, it's not considered to be a chemical reaction because it's just a phase transition. There is no bond breaking or bond formation here, so that it's not considered as chemical reaction. And like even dissolving in a water is not even considered as a reaction, because this substance, the sugar, be intact in H2O. So we cannot consider this to be as reaction because there is no bond breaking or bond making here. So apart from this, if the chemical reaction has bond making and bond formation, I mean bond breaking and bond formation, then it's even a new product should be formed. That's considered to be a chemical reaction apart from phase transition or without any bond change. And here those are considered to be the chemical reactions. And now we could get into other. Okay, now we can go into the chemical reaction. Actually, let's actually take a generalized chemical reaction form that's can be unfamiliar for most, but it has an understanding. Alpha R1 plus beta R2 plus and so on, and gives rise to P1 alpha plus P2 beta plus and so on. This is one of the generalized way that we could write for a reaction where these are reactant and these are products after the reaction, and here these are can be considered as molecule, as it's a molecule. And you could think that after reaction the same molecule arise, but here we could actually change the coefficient actually express the number of moles for the reaction that could occur. And this way we could actually keep this to be zero. As I prioritize understanding, it's actually easy to understand now. This the generalized way of reaction that we could write, and these are the it's reactant, and the after the reaction it's become a product, and they are the coefficients. Now, as we consider for this reaction, the rate would be this way: the change in concentration of R and to the time, and it's divided. This equation actually, I mean this term is actually divided with R1, and there is a negative sign because actually here it's on reactant side. As the reaction goes on, the concentration actually decreases. In order to make the rate of reaction positive, rate of reaction should always be positive, and in that regards we actually need to take the negative side, and this is actually what happens. And the reason why actually we need to multiply R1 is to actually get a unique value of the reaction which is independent of the concentration terms chosen. And I would explain what actually this says. And this is the term that which one of the text that which I have referred have written. but they didn't explicitly explain the reason. But I like to give an example in order to understand. And now this is the way we actually understand it. By considering this reaction itself, this is just a reaction. What actually happens in if in reality actually we actually contain, let's say we have certain reactant, and it reacts and gives a product something like something, okay, and here we got product. In reality, this is what happens, but there are many millions or billions or trillions of reactions happening according to the substance amount of substance we have taken we take, and this actually happens. uh, let's take initial concentration of alpha molecule as A, and the product concentration would be zero because the reaction doesn't takes place. And actually here I am only considering this reaction because this is a generalized reaction. I cannot take it. I It would be a mistake to only consider a single molecule to another molecule because the reaction is generalized. I would like to take a reaction like this: alpha to uh, delta product. Let's say this to be 4. Yeah, R1 alpha to P4 delta. I would like to write it separately here. And this what actually happens for this reaction: the product of delta, I mean the concentration of delta initially would be 0, and as the reaction pass after time t, let's take time t, at this particular time the concentration would be R1 x. I will explain why this actually happens. And here P4x comes, and here what actually happens is with this reaction, I mean for this reaction, R1 moles of alpha will actually become T4 moles of delta. This is actually a standard. Let's Even though I have chosen this reaction, but this, if it is a law in nature, let's consider this to be a law. And for R1 moles it will become P4 moles. And here, if for total concentration, let's say alpha, with this concentration there is a certain amount of concentration taken out at a time t, and this time t concentration that which have been taken out from initial concentration is taken as with the moles. We need to be considering that let's x moles of have been taken, and it should be multiplied with r. In that regard, we could actually find that r1 into x moles actually taken out. And as we consider concentration, there is a hidden factor in it, as this is considered at constant volume. But yeah, this is not generally explicitly explained, but here the consideration of volume is constant in order the act of measuring moles. As I earlier said, we need to consider concentration here. Even though we explain it with moles, here there is a constant volume. In that regards, I am explaining this simplification. And here R1 into X will itself should become P4 into X. This is the same way as writing R1 moles will become P4. But here there is a certain amount of X that which actually uh, goes this way. With numericals it would be easier to understand, uh, but X is just a variable because we don't know actually the reaction, and it's just a way to understand it. And now at a final reaction it would be 0, and it would become p4. And this is what actually happens for final concentration, but we actually write this as a way. I mean, the actual reaction, what happens is R1 concentration itself becomes P4. Finally, let's take even though, and here it is R1. If we take for 1 liters, and this is P4 if you take for 1 liter, but it could be a B value which we don't know. I mean, by don't know, I mean that it is considered as a variable. This is just a understanding that which we need, and what actually happens according to the time to the reaction. Apart from this, actually, uh, if we work out on this way of understanding, you could understand, even though at the first sight you may not understand. By listening repeatedly or by thinking yourself, you could understand what actually happens here. And now um, we have actually, and now we take the rate of disappearance of alpha is taken as change in concentration. Let's take for this itself, when we consider t is equals to 0 here, and for here t, and now the disappearance rate of disappearance comes with minus, and taking alpha concentration earlier as a, I mean final concentration should be subtracted from final concentration to initial concentration. As we subtract, we get minus r1x divided by the time t, and in this way we get a positive value. This is actually the rate of disappearance of alpha. When we consider rate of disappearance of alpha, the rate of reaction is not the same as rate of disappearance of alpha. Even rate of appearance of beta is equal to positive. Here what actually happens increases, it increases to p1 x p4x p4x divided by t. This is the rate of appearance of beta, and this is the rate of disappearance of alpha. These two are not rate of reaction, because uh, reason this rate of disappearance is divided with its quotient in order to get a unique value of the rate of reaction, which is independent of the concentration terms that which we have taken. Means actually we have taken a as a concentration, we have chosen it, and for this molecule alpha, uh, here the R1 is actually the coefficient of alpha. Without considering this, the rate of reaction here for this equation, we need to only consider the actual x value here. This is considered as rate of this reaction, because rate of appearance and disappearance can be different for each molecule, but overall if we consider for this reaction, the rate of reaction is this, it's x divided by t. It's a unique value that which we could get, which is not dependent with the uh, product side or reactor side, which is independent. So with this order, to get rate of reaction this way, we need to actually divide it with minus delta alpha divided by delta t, and this is divided with r1 in order to get xt, and plus delta beta divided by p4 delta t in order to get xt. It is not in order to get xt. If we actually uh, think in a circular form, To get this as that or the actual understanding, it's actually interlinked with them both itself. So this is the way that which we actually can manipulate or understand this way. And now let's consider a graph. Here the graph is in y-axis, we take concentration and time. This what actually average rate is. uh, the average rate actually implies we actually didn't take at this particular instant there is a rate for this particular time, but average rate actually makes the difference with the concentration at two different time. And by taking the definition of rate, we actually find the rate of average, average rate, not an instant rate. Instant rate is another story, and there is an analogy with velocity for this to explain, but we are not going to that now. And this is the way actually occur. And here let's take what is instantaneous rate. The simplest definition for rate actually explains things well, but as we need to increase our understanding, the instantaneous rate is what at a particular fixed time we get. uh, this is actually this way of representation, this way of understanding comes with calculus, and where we use differentiation here. And how actually in differentiation it is represented this way. If we consider a reactant R, let's take R, capital R, and with a particular time, at this particular time dt, the rate of reaction, the concentration change in concentration would be this particular thing, and the rate would be instantaneous at that particular time. This is the way actually we could find the instantaneous rate. And this is what instantaneous, which is different from the simpler explanation or the formula that which we actually given for the rate. And for this itself we could write instantaneous average, and for product the instantaneous rate would be dp divided by dt. And we have actually discussed regarding rate, and now let's get into certain laws and expressions that which actually comes in chemical kinetics. Earlierly, there was a understanding that which arises or conclusion scientists have found that regarding law of mass action, regarding chemical kinetics, which is law of mass action. What the idea earlier was that at a given particular temperature, the rate of a chemical reaction, it will be chemical reaction, and the rate of that chemical reaction is directly proportional. Directly proportional in the sense, I don't like to give the analogy, but I would say the if the rate increases, the particular thing that which is directly proportional increases. If rate decreases, the thing that which is directly proportional decreases. Now that thing here, according to law of motion action, they have said concentration of reactant. That's what they actually said. And according to law of motion action, uh, there is a constant here. It's called uh, we in mathematics we could remove directly proportionality, and we could equate the both thing, both dependent thing with a constant. With that constant itself, these two are related. There may be many things, if we didn't consider everything. If the rate is only directly proportional to concentration of reactant, then itself we could just multiply with constant. If the equation actually becomes complex, when we consider temperature and other factors which influence the rate of reaction. But as earlier, the law of mass action is simpler, as we express here. The rate is directly proportional to the concentration of reactant, and this rate is equal to a constant K and a reactant. Why actually this K comes, I will explain later if possible. I don't know. Uh, this is how the rate actually be equals the rate constant and multiplied with reactant, and here it's a rate constant, and this is what law of mass action says. And actually this is not an experimental way. It is a pre-form idea that earlier scientists had, and this was advanced. I mean, this was advanced by knowing the mechanism of the reaction. By knowing the mechanism of reaction, they get to understand that for every, they have first primarily taken consideration that every reactant's concentration is, uh, every reactant concentration makes the rate of reaction. But by knowing the mechanism, we later scientists were able to find that the rate of reaction doesn't depended on all the concentration of reactants, but only few, because mechanism explains that. And this is where actually order of the reactions come, where the I will explain by the mechanism. This is the second thing chemical kinetics actually expresses in order to. And by considering the mechanism, there was another law which arise. It's called a rate law, and this actually explains that every concentration of reactant doesn't depend. What I'm what I like to explain is that now we have now rate law. I would take an example equation which is most often used to express rate law. N2O5 gives rise to N2O4, sorry, NO2 plus O2. This is the most familiar equation when we express the rate law. Here, according to law of mass action, the rate can be this way. And actually, law of mass action has limitation. If this equation is considered to be the basic, elementary reaction, we call it elementary reaction, where this is a standard reaction, mechanisms reaction, where it is fixed. But the law of mass action doesn't actually says regarding elementary reaction, but rate law express through experimental values and analysis. We could get to understand that this is the elementary reaction, and this is what the elementary reactions reactants concentration is what we should be taking. And it could be a 4 even if we take 4 as the coefficient of NO2, and it's considered to be an element reaction. And this is a flaw with law of mass action. That's why the red law is most advanced, a little advanced from the law of mass action. And now this is the mechanism where this equation and the rates that which comes with it. And and now we could go with the order of reaction. For this reaction, the order is 1. By experimental values, we could get that the power of N2O5 is 1. And for this reaction, the mechanism is actually what actually really happens, as experimentally found, that N2O5 actually breaks down into NO2 and NO3. and here the NO3 is unstable, and NO3 again reacts with other molecule of N2O5 and gives rise to NO3, I mean NO2 plus O2. And this is actually, these are elementary reaction that which takes place, but generally we could write this way. And here these are the two elementary reactions that which occurs with the generalized reaction, and this is what the mechanism of the reactions. And here this reaction is slow, I mean slower, and this is faster. After this is NO3 is the mediator where it actually fastly reacts and gives a product out, and here this is the slow reaction and slow element reaction. In this regard, we could find that the rate is only actually dependent on the concentration of NO2 itself. In this regard, this is the formula for the rate at which we get, and here the concentration of, I mean the power of N2O5 is 1. In the way we call it as first order reaction. And there are four orders of reaction: zero order, first order, second order, and third order reactions. And by the mechanism we could actually get first order or second order or third order reactions. There is another idea which is molecularity, where actually for a particular reaction, for this reaction, if we consider the molecularity of this particular reaction, molecularity is nothing but the number of reacting species in a chemical reaction. And here if we consider this reaction, and we could take, there are two molecules N2O5, and the molecularity of this reaction is 2, but it's incorrect. The reason because is here the mechanism is different, and here it happens in 2 steps, and here for this elementary reaction itself we could find the molecularity. Here the molecularity for this reaction is 1, where one molecule of reacting species is available, and here for this reaction the molecularity is 2, and there are two molecules of where the reaction actually occurs. And this way, this is the idea of molecularity and its definition. The rate of reaction actually has certain factors which actually influence the rate of reaction. And here first primarily we have already, I mean we have taken the definition of rate as concentration, where the rate is explicitly uh, dependent on concentration. And now the rate also has other factors that influence it, is the temperature. It's actually roughly said that for every chemical reaction that uh, most of the chemical reaction that the as the temperature increases by 10 degrees Celsius, the rate of reaction actually doubles. And there is another factor that which influences the rate of reaction, is the nature of reactants and products. And there is other factor which is the presence of catalyst and surface area and exposure to radiation. These are the factors that could actually uh, change the rate of reaction. And there was other thing that which I forgot to explain, is that law of mass action and rate law. These both laws actually express that rate of reaction, right, at particular concentration, and this is instantaneous rate, not average rate.